Hey everybody, I hope you're having a good day. This is a lecture over, well, membrane transport. And the way that we're going to be talking about this is we're going to bring it back to something that we're already a little bit familiar with, and that is our mechanisms and classifications of enzymes. Specifically, we're going to be focusing in on classifications of enzymes. Now, if you remember from our previous discussion of the classification of enzymes, we had a grand total of seven items, seven classes, but we really only investigated six of them. Now, as a little bit of a review, every single enzyme will fall into a category, into a general category, and these are designated as EC and then a number. Now, if you remember, every single enzyme is grouped in this fashion with the first digit or first number characterizing kind of the general class, and then the second digit, the third, and the fourth, indicating the specific enzyme. I believe that I mentioned this. I always kind of think about it like an IP address or an Internet Protocol address. That's remember that's what IP stands for, not intellectual property. But in this case, it an address effectively. So this first digit tells you something about geographically where a computer is located. The second one would kind of narrow that geographic scope a little bit. So the first one would say like, oh, well, this computer is in, let's just say, North America. Okay. And then this computer is in Mexico would be the second group of numbers. And then you'd maybe have like a little bit more of a precise region, but rather than region, it would be like, oh, well, Xfinity is the internet service provider, and this computer is number 72 on Xfinity. Now, that's probably a both inaccurate and a entirely too simplified idea of something very sophisticated like an IP address, but effectively that's what an EC is. So, our first number tells us that the enzyme is an oxidoreductase or a transferase or a hydrolase. So every single enzyme is going to be like, okay, EC 1, and then the second digit would say something like, well, this is an enzyme that acts on, you know, carbonyl groups. So this tells us a little bit more about that specific enzyme. It is an oxidoreductase. This is the functional group that it works on. And then it uses the electron carrier, something like NAD plus slash NADH. In which case you'd be able to say, okay, well, oh, and then the last digit, I'm going to switch my variable and just call it Y. This last digit is, oh, well, we are specifically talking about something dehydrogenase. So that's kind of the lay of the land. Now, in the event that rather than working on a carbonyl group, this enzyme worked on, let's just put it simply, let's say an amine. Well, rather than being, but it's still used in NAD plus and NADH. Okay, well then the categorization, the classification would be a little bit different. Now, I mentioned previously that what I want you guys to know is I want you to know oxidoreductases, transferases, hydrolases are 1, 2, and 3 respectively. Lyases, isomerases, and ligases are 4, 5, and 6 respectively. Lyases add or remove a group. They may break a carbon-carbon, carbon-nitrogen, carbon-oxygen, or carbon-sulfur bond. Isomerases rearrange the atoms. And last but not least, ligases make COCSCN or CC bonds using ATP. And that this is a little bit more refined definition of what we talked about with respect to ligases. Um, it's using ATP. It's in the sense that ATP is the energy source. So it's almost like um, the way that I always kind of think about it is that ATP hydrolysis takes place, and then in close proximity to that is our desired reaction, and it kind of captures some of that energy and drives it. So it's almost like um, you want to fly to the moon. So what you do is you say, okay, well, I'm going to detonate some TNT, and I'm going to be standing on top of a piece of metal, maybe not a piece of metal. I have my spaceship that I'm going to place over that dynamite, that TNT. Um, Not the best example because that would probably only be fatal, but that's kind of the point, not the fatality. But that's the point of harnessing this energy. So this TNT detonates, and then you happen to be next to it, and you go up in the sky. Um, Without that TNT, you're not going to be able to lift yourself off the ground spontaneously. So without the ATP hydrolysis, that reaction is not going to take place. Now, number 7 is a translocase. We need to move ions or molecules across a membrane. So our 7th group are translocases. Now, this is relatively new. I think that this group was conceived in 2018. And essentially, what it was okay, well, we know that this is taking place. There are ions or molecules that are moving across the membrane. How's that taking place? How is it happening? And usually, it's in complexes that have several different reactions taking place. But ultimately, it was decided by I believe it was IUPAC, um, which I know that that's IUPAC. I remember that being a very important acronym in Gen Chem 1 and in organic when you learned about standards, and IUPAC being I guess, kind of the governing body that decides this. Okay, so translocase, this illustration is what you need to know because we're moving across a membrane. This isn't something like, oh, well, it's moving from one side of a cell to the other. No, a membrane is an essential part of a translocase. So this molecule, and notice how this, where I've got my star, I'm going to go ahead. Now it looks like an over easy egg. This doesn't necessarily have a charge. It could be positively charged. It could similarly be negatively charged. At the same time, it could be neutral. It could be totally neutral. Ions or molecules are what are moved across a membrane by a translocase. Now, for our classes of enzymes, here's all of our 7 classes: oxidoreductases, transferases, hydrolases, lyases, isomerases, ligases, and translocases at the bottom. Now, the important part about all of these is I want you to notice we've got not necessarily equilibrium arrows or no equilibrium arrows, but I want you to think about these all as reactions that are being catalyzed. The one at the bottom here, well, we have a reactant and we have a product. The difference about our reactants and products here is that our reactant is, well, it's found on one side of the membrane, and then our product is found on the other side of the membrane. So think about this as molecule A is the exact same. The molecule does not change. The only thing that changes about it is its location. And when we look at a translocase, we're thinking, what is the concentration on one side of the membrane versus the other side of the membrane? Now, membrane transport is the transport of molecules. It can be either mediated or non-mediated. There is what is known as non-mediated transport. This is something known as simple diffusion. So effectively, this is something that H2O or O2 or some hormones will freely move across a membrane. So they can diffuse across a membrane. So they're going to make their way from one side of the membrane to the other side of the membrane without any sort of intervention. They will be able to just kind of sift straight through. Now, the rate of that diffusion depends on the concentration gradient and the substance's solubility in the membrane's nonpolar core. Because remember, when we talk about a membrane, we're talking about a lipid bilayer. We've got a polar head group, and then we've got our nonpolar tails. So if this is what our membrane looks like, well, something might be attracted to the polar head group because it's similarly polar. But as soon as that polar thing enters kind of the central cavity of that lipid bilayer, well, then it's going to be greeted by something that it's unlike. So a polar molecule in a non-polar core, the solubility is typically going to be fairly low. So in order for something to move across a membrane, it has to kind of, I'm going to put a smiley face, it has to like this part of the lipid bilayer, smiley face. It also has to like this side of the membrane, this side being the internal core. And another aspect of that is that it has to like it enough, but also dislike it enough that it doesn't stay in there. So we don't want something that's going to be non-polar to enter the lipid bilayer and just set up shop and stop there. It's got to start, move through, and then continue moving through. Water, oxygen or O2, and steroids are typically the molecules that will diffuse very readily. Now, another type of transport known as mediated transport. There are two categories depending on the thermodynamics of the system. There's passive. This is mediated transport or facilitated diffusion. Molecules flow from high concentrations to low concentrations. There is also active transport. A molecule is transported against its concentration gradient. When we talk about translocases, this active transport is kind of what you want to be most aware of. This endergonic process must be coupled with an exergonic process to make it thermodynamically favorable. So this is where something like the hydrolysis of ATP would release energy to kind of like shoot something through a membrane. Now, this is taking place across a membrane from one side, the source, to its destination, the other side. Now, I think that this is a worthwhile thing to remember because back to our idea of a lipid bilayer, one of the things that I mentioned was I use the terms inner leaflet and outer leaflet. And when it comes to the question is, well, is this on the inside of the membrane or the outside of the membrane? Being on the inside of the membrane would be like it's close, it's in the cytosol. The outside of the membrane would be the extracellular space. So we've got our inner leaflet, outer leaflet. We've got the cytosol versus the um, extracellular space. So that's kind of the path. Now, with respect to something moving across a membrane, we have to consider a couple of different things. Well, the difference in the concentration of substance on two sides of the membrane generates what's known as a chemical potential difference. So basically the question is here, well, is the concentration in the destination, the site that it's going, is it higher or lower? Simple question. Now, we compare that to the source. So that's where, whenever you say higher or lower, you're comparing these two places. Is it higher in the cytosol or in the extracellular space? And is it lower than that? So this is our way of evaluating, well, is this energetically favorable? Is this spontaneously going to happen? So think about this as you could have something that goes from a high concentration, so the source is high, and the destination is low, which is going to lead to a negative delta G. Okay. Now, this right here is in a vacuum because this is only looking at the concentration. And keyword here is substance. Notice how this doesn't say anything about the makeup of what that substance is. This is what is the concentration of that substance in versus out. Is it high in and low out? Is it low in? Is it high out? That's the question. Is it equal? Well, let's think about this. If the concentrations are equal to one another, RT, ln, 0. That's going to, if the, or sorry, not 0. I got ahead of myself there. The natural log of 1 is going to be 0. Okay. So if you have, I always just try to think about this in a very blunt fashion. Is the concentration higher or lower? And then compare those two and come up with like a nice kind of raw number and say, oh, okay, well, based on it being 10 over 100, okay, this is going to be a negative delta G. Okay, now that's one aspect of it. The other component here that we have to account for is the movement of ions. Okay, so we're defining that substance. Defining and basically saying, okay, well, we're talking about the movement of ions across the membrane also results in a charge difference. Okay, but let's think for a second there. So we're moving ions from one side of the membrane to another. What makes an ion different from, and I always like to come up with let's say a sodium ion versus a glucose molecule. Well, the fundamental difference between those two is one is charged, one is not charged. Okay, so a sodium ion has a positive charge. A glucose molecule has no overall charge. Now, that right there alone is going to generate an electrical potential difference, which we have to account for and which we can calculate using the using Faraday's constant. So that is known as our electrical difference. And we combine those two things together to make this equation right here to look at what's known as our electrochemical potential. Delta G equals RT ln of the concentration of our species in the destination versus in the source, plus Z sub A, which is our charge of our ion, Faraday's constant, 96.485 kilojoules per, or kilojoule per volt mole, and then delta psi, which is our membrane potential. Just one second. So this gives us a mechanism to relate the concentration as well as, well, is moving an anion or a cation favorable. Now, the charge is going to be, well, pretty simple and straightforward. If the question mentions, or if you see a scenario that says, well, Na plus, well, that's simply going to be +1. If we're moving magnesium 2 plus, well, then that's going to be +2. If you are moving, say, a chloride ion, got to change that, magnesium +2. Okay. If you are moving a chloride anion, your charge is -1. So you do take into account the magnitude of that charge. Now, our delta psi, that is something that is unique for basically every single ion. Whether or not it is a potassium ion or a sodium ion, you're going to have different values for those different ions. Now, this is an example of how that kind of plays out, and some important things to know about this membrane potential. By default, delta psi is measured as the potential inside minus outside. Okay, so this delta psi value is based on that. So what's important to notice about that delta psi value that you would be provided with in a question is that is going to be something that can be a negative 54. It can be a positive value. Now, with that in mind, a negative value indicates the inside of the cell is more negative than outside of the cell. If an ion moves from the outside to the inside, then the membrane potential is fine. What that means is that if you're prompted with, hey, the membrane potential delta psi is 32, positive 32. When it says that is fine, that means you do not change that value. If an ion moves from the inside to the outside, however, then the sign of the potential must change. So what that means is this scenario would be ion X, we'll say, with a +3 charge, moves from in to out. So thinking about that as, well, this ion is being released, or this ion is being exported. If you're given a delta psi of 32, well, then you'd say, oh, okay, well, this is going from the inside to the out. That means that this delta psi needs to be -32. You would change that. Now, almost always the cytosol is considered the inside of the cell. There are, however, situations where that would be different, and you would be prompted with that in the question. Now, if more than one ion is transported, calculate the free energy change for one ion, then multiply for additional ions. It is more favorable for a charge, from a charge standpoint, to transport a chloride ion into, or sorry, is it more favorable into when delta psi is negative 60? Okay, so we are going in, okay, into. So if we have, let's go ahead and look at this and basically process this question. Now, the first things first, is this asking us for this entire electrochemical potential difference? Kind of, but not really. Um, the kind of is because it's asking, well, is this favorable or not? And we're asked about an ion, but not really because we don't have any of this information or this information. So effectively, this part of the equation is not part of what we're doing. Instead, what we want to do is we want to say, okay, well, we're taking a chloride ion, -1. Faraday's constant. I'm just going to plug that in as 1. It's provided here, 96.485 kilojoules per volt mole, but for the purposes of this calculation, we don't really even need to think about that because we're asked kind of a binary question. Is it favorable? Yes or no? And then we're given a delta psi value. A delta psi value, I just erased that 1 because I don't really care about it that much. -60 millivolts. Okay. If you look at it right here, delta G, well, that's a negative times a negative, which would be a positive. Okay, but the question is, we're going into. Okay, so what does that mean? We have to think about this delta psi value. It was provided to us as -60 millivolts, but we have to think about the directionality, the orientation of this. This is going into, so it's coming from the out to the in. So what does that mean with respect to our delta psi? Do we change it? That's effectively the question that we're trying to answer. And since we're going into, or in other words, going from the outside to the inside, no, we don't change it. In which case, this would be a positive delta G, because negative times negative. So then my question is it favorable? Well, by virtue of it having a positive delta G, no, it's not. Okay, the next question here, what about transporting it out? Well, that's just the opposite. Okay, so what do we have to do with respect to that opposite? Well, our delta G is -1 times, oh, now we got to switch that value. That's plus 60 millivolts, in which case our delta G is going to be a negative value. So I'm going to change this, and I'm going to say unfave, fave. Okay, so that is just analyzing the membrane potential difference based on the electrical potential. Now, when we're transporting something across a membrane, we've got a lot more things to consider. So over here, transporting a sodium ion in or out of a cell when our delta psi is -60. Okay, so what we're doing here is we're accounting for everything. What is the change in free energy associated with transporting sodium into the cell? Okay, so we're going in. So let's just look at this first. We have a positive ion. A delta psi is -60 millivolts. Okay, so let's go back. We're going from the outside to the inside. So we are going to keep that membrane potential. So from a standpoint of electrical potential, this is negative delta G. And so from that angle, it's favorable. And that's indicated right down here with the electrical potential. Now, the other aspect of this is, well, right here. We are looking at our destination versus our source. Okay, so this is going in. So what that means is our destination is 12. Our extracellular is 145. Make sure that your unit's millimolar, millimolar. So if you have a calculator, plug all this in, and what you'd do is you'd get natural log of 12 over 145. 12 is our destination, the cytosolic concentration of Na plus, 145, which is our extracellular concentration of sodium, and that's 145. So 12 divided by 145, okay, natural log of that. Well, that's going to give us a negative value. And then we multiply that by our RT, which in this case, 0.008315 times 310 times the natural log of 12 over 145, we get delta G there. And then to kind of bring this back together, we did this part of the calculation first. We figured out that yes, it was a negative delta G. And this is a negative 6 delta G. Great. Okay, so when we transport sodium from the outside to the inside of a cell, from electrical potential measurement, it's favorable. From a chemical potential angle, it is also favorable. So what does that mean? That just means it's favorable in both aspects. Now, this question right here, it's the exact same thing. The only difference is we're talking about transporting sodium out. Okay, so what's the fundamental difference that we have to account for? Well, from the electrical standpoint, that means that our delta psi is not 60 millivolts. Instead, it is a positive. It's not negative 60 millivolts. Instead, it's positive 60 millivolts. Converting that into volts is going to be 0.06, which is still a positive value. So this is unfavorable when we are transporting out. Well, then, what else is different? Our concentrations. Our source is now the cytosolic concentration of sodium. Our destination is the extracellular concentration. So that's 145 over 12. So that too is unfavorable. Now, this is at the heart of what this sort of calculation entails. And that's the complexity of it is just a question of, and I think that the best way to approach this is to look at it as, okay, is it favorable from this standpoint and is it favorable from this standpoint? And if your answer is yes, it's favorable from both standpoints, then great. It's going to be kind of doubly favorable. It's going to be a compounding level of favorability. If it's unfavorable from the electrical potential and then it's favorable from the chemical potential, but then you've got something that you got to reconcile, in which case there is a value of doing all those sort of specific calculations. Now, with that, we can go ahead and proceed here to look at different membranes. So here what we have in different transports. We have two major modes of transport, primary active transport and secondary active transport. Now, the important thing about this is to understand all the different species that are here. So what we have is our molecule X. This is inside, this is outside. We're not looking at what is this specific molecule. Instead, we are looking at this as, okay, this is just some random molecule. It might be an ion, it might just be glucose. And if it's just glucose, well, then that doesn't have a charge. So this shows us that from a chemical potential, we know a little bit about our concentration inside the cell versus outside the cell. Well, inside of the cell, our concentration is very low. Outside of our cell, our concentration is very high. So inside the concentration is low, indicated by only a single X being on the inside of the cell. Meanwhile, outside, we've got a ton of it. So from the chemical potential standpoint, this is unfavorable. So this X is not going to be able to move across this membrane by just its desire to, because the concentrations are unfavorable. They are kind of mismatched. What we can do, however, is we can use the hydrolysis of ATP to ADP in inorganic phosphate. So ATP is hydrolyzed to make ADP and PI. That reaction releases energy. And it's almost like this is that TNT that explodes and propels this X against its concentration gradient. So whether if X is an ion, okay, cool. If X is an uncharged molecule, doesn't matter. In either way, it's either chemically unfavorable or electrochemically unfavorable. You need this ATP hydrolysis in order to get that to actually move across the membrane. Now, that is a single protein that's doing that. Okay, so that's primary active transport. So we have the activation, basically, of this ATP hydrolysis that uses a single protein to move it. Our secondary active transport. Okay, secondary because we've got two proteins. Now, with that in mind, we have this protein X, which is again unfavorable to move across its gradient. Now, we've got two things taking place. We've got X moving across the membrane, and we've got S moving across the membrane. Now, what I want you to notice about both of these, X, S, X, low concentration to high concentration, unfavorable. S, going from the outside to the inside, so it's a low concentration, to high. So we've got these two things that are kind of both moving against the, or in the opposite direction of as you would want. Now, that is known as secondary active transport because what we then have is ATP hydrolysis that is going to move X from the low to the high. So X moves across because of ATP. That ATP hydrolysis drives it. Okay. S, by comparison, this protein right here moves S across the gradient. It does not use ATP hydrolysis. But instead, let's look at X. X's movement from out to in. Well, X is now favorable. Moving from the outside to the inside, that is favorable. And what it's going to do is it's going to basically bring S along for the ride. So this is what is known as a syn-porter. It's moving, it's almost like X moves from here to here. It likes to do that. It's good to do that. That's a favorable movement for X. S just kind of rides the coattails of X from one side of the membrane to the other side of the membrane. So that's our secondary active transport. So if you think about this as, well, what's the point? The point of this model on the right-hand side is to move S from the outside to the inside. Okay, how is that happening? Well, it's by using two different proteins. We are not so much interested in the first protein, but we're interested in the second protein. So S is moved with what's known as secondary active transport. Now, with that in mind, I want you to be familiar with this protein complex right here. This is known as a sodium-potassium channel, or pump. And what this protein is going to do is it's going to take 3 sodium ions from the inside of a cell and move them to the outside of the cell. When you see a model like this, it's very difficult to, process all the information at once. So you got to break it down into simple points. So the simple point is 3 sodium ions are going from the interior of the cell to the exterior of the cell. Okay, so that is one kind of objective. Now, one of our next objectives is to say, all right, well, what else is happening? We're taking 3 sodium ions and getting them out of a cell. We're also taking 2 potassium ions from the outside and we're bringing them in. We're kind of counterbalancing them. So this is why, if ever you heard of the term electrolytes, these are great examples of electrolytes. This is why when you drink Gatorade, you get lots of potassium. You want that potassium because you've kind of got to offset the removal of that sodium. And you've got to have like electrical potential difference between what's inside of the cell and what's outside of the cell. So you want that charge differential, and this is how you're going to accomplish it. So 3 sodiums out, 2 potassiums in. Okay, great. Now, what else is happening is a couple of different things. I want to highlight this right here. E1. That is our enzyme that is doing this. Now, E1 kind of undergoes a little bit of a transformation of sorts. And if you remember back to when we were talking about mechanisms, one of the mechanisms that we talked about was a ping pong mechanism. In a ping pong mechanism, an enzyme binds to something, forms a different version of itself, and then can bind something else. That's effectively what we have here. E1 is our enzyme. E1 binds ATP and 3 sodium ions. Okay, so E1 can bind the 3 sodium ions, and when it does that, then it can bring on ATP. It hydrolyzes ATP and transfers one of those phosphate groups to itself. So this E1 with that tilde P, that's kind of our different form of E1. This is still bound to those 3 sodium ions, and this is the form of our enzyme that can undergo a change. And whenever it undergoes a change, it kind of repositions where that sodium ion is and is able to release it on the exterior of the cell. So now what we got is E2, our phosphorylated version of our protein that doesn't have sodium bound. That E2, or that phosphorylated E2, then is able to pick up our 2-potassium. So our phosphorylated E2 binds to potassium, and then what it does is it's going to release that inorganic phosphate, that Pi, and it's going to be E2 plus 2 potassium ions. Those 2 potassium ions and E2, our different form of our enzyme, will now undergo a change where it can release 2 potassium ions on the interior of a cell. So this, in a nutshell, brings into a lot of different, or brings up a lot of different things. We've got our ternary mechanism, or we've got our ping pong mechanism, and we've got kind of different forms of our ping pong mechanism. It's not quite as trivial as, well, this binds this and then it binds this, or this binds this and undergoes this change and then it does this. That's kind of what we have in the sense that E1 will bind sodium. Okay, so it's holding on to it. The free E1 will not bind ATP. It will only bind ATP whenever it has those 3 sodium ions. Okay. Then ADP is released, and most importantly, E1 gets phosphorylated. That phosphorylated form is the way that I think about our different form of our enzyme. Now, that different form of our enzyme E1, whenever it's on the exterior, it has released the sodium ions. Now it forms E2 phosphorylated. That phosphorylated E2 can bind to potassium ions, and boom, it's going to hydrolyze that phosphate and release and make our E2 with our 2 potassiums. Okay, so this is it's pretty dense and complicated, but I don't think that it's overwhelming. I think that when it comes to those electrochemical potential calculations, you just have to take them piece by piece. And whenever you do that, you're going to set yourself up to ask yourself binary questions like, is this favorable in this direction or is it in this direction? Is this favorable from a chemical potential difference? And is this favorable from electrochemical or electrical potential difference? So work through those practice problems. Just kind of take them all and say, okay, well, what if I switch this from a cation to an anion, or to an anion? And then if I said that it was going from the outside to the inside, how would that change my result? At any rate, I hope this is helpful and I hope you have a good one. Bye.